In the darkness of a February night in 1943, 13 British bombers climbed into the freezing sky over England. Inside their bellies, beneath layers of armor plating and fuel tanks, sat a device that would change warfare forever. The crews called it by different names. Some knew it as the navigation miracle. Others whispered about the secret weapon. But officially, it bore the cryptic designation H-2S, and what it could do seemed impossible. It could see through clouds, through darkness, through the very fog of war itself. And on this night, as those bombers turned toward Hamburg, Germany, they carried with them the power to strike with precision in conditions that had, until that moment, made bombing little more than expensive guesswork. But this story doesn't begin in the clouds over Germany. It begins in the smoking ruins of British cities, in the desperate mathematics of failed bombing raids, and in a decision so controversial that some believed it would hand Britain's greatest technological secret directly to Hitler. By early 1941, Britain stood alone. The United States hadn't yet entered the war. The Soviet Union and Germany were still bound by their non-aggression pact. And night after night, German bombers rained destruction on London, Coventry, Birmingham, and dozens of other cities. The Luftwaffe had turned British cities into testing grounds for a new kind of warfare, one that deliberately targeted civilian populations to break national will. Britain's response had to be strategic bombing, not because it was the most humane option, not because military planners thought it would end the war quickly, but because it was the only way Britain could strike back at the German heartland. The British Army had been evacuated from Dunkirk. The Royal Navy controlled the seas, but couldn't bomb factories. Only the Royal Air Force's Bomber Command could carry the war to Germany itself. There was just one problem. Bomber Command was failing catastrophically. The official reports from bomber crews returning from night missions over Germany painted pictures of devastating accuracy. Pilots reported dropping their bombs directly on target. Navigators calculated their positions with confidence. Bomb aimers claimed to see their explosives impact exactly where intended. The photographs taken by cameras automatically triggered when bombs were released seemed to confirm these claims. But those photographs, when analyzed carefully, told a very different story. In August 1941, a civil servant named David Bensusan Butt was assigned to review 633 photographs from bomber missions over Germany. His task was simple: verify that British bombs were hitting their intended targets. What he discovered would become one of the most important and devastating documents of the entire war. The Butt Report, as it came to be known, revealed that only 1 in 3 aircraft claiming to have bombed the target actually got within 5 miles of it. 5 miles! In the heavily defended Ruhr industrial region, the heart of German war production, the figure dropped to 1 in 10. On moonless nights, it fell to 1 in 15. Let those numbers sink in for a moment. 90% of bombs dropped on the Ruhr were landing more than 5 miles from their targets. They weren't hitting the wrong factory. They weren't damaging the wrong part of the city. They were landing in empty fields, forests, and farmland. Bomber Command was spending enormous resources, losing aircraft and precious trained crews, dropping thousands of tons of explosives on Germany. And most of those bombs were hitting absolutely nothing of strategic value. The implications were staggering. Britain was spending roughly 1/3 of its entire war production on Bomber Command. Thousands of young men were training for years to become pilots, navigators, and bomb aimers. Factories were churning out increasingly sophisticated 4-engine heavy bombers, each one a marvel of engineering that cost as much as a small warship. And for what? To plow German farmland with high explosives? Some voices in the British government called for Bomber Command to be scaled back or even disbanded. Why waste resources on such an obviously ineffective strategy? Why continue to lose crews at unsustainable rates for minimal results? Winston Churchill himself began to question whether the bombing campaign could continue. But Churchill and his advisors understood something crucial. Britain needed to be seen as fighting back. The British public, enduring nightly bombing raids themselves, needed to know their country was striking back at Germany. More importantly, Joseph Stalin was demanding that Britain open a second front to relieve pressure on the Soviet Union. An invasion of occupied France wasn't yet possible, but strategic bombing could tie down German resources, force them to divert fighters and anti-aircraft guns from the Eastern Front, and demonstrate to Stalin that Britain remained an active, aggressive ally. The bombing campaign would continue, but it desperately needed to become more effective. The problem wasn't courage. British bomber crews were among the most heroic servicemen of the war, facing odds that made their survival rates comparable to frontline infantry in the worst battles of World War I. The problem was navigation. At night, over enemy territory, with German fighters hunting them and anti-aircraft fire exploding around them, navigators using traditional methods were simply guessing their positions. Those traditional methods included dead reckoning, calculating position based on speed, heading, and time elapsed since the last known position. But wind would blow aircraft off course. Pilots would dodge flak, changing heading constantly. Navigators would peer into the darkness below, looking for landmarks. But on cloudy nights, they couldn't see the ground at all. Even on clear nights, German cities observed strict blackout discipline. No lights betrayed their locations. The only reliable navigation aid was celestial navigation using a sextant to measure the angles of stars. But this required clear skies, a stable platform, time to take measurements and perform calculations, and the luxury of flying straight and level. Something no pilot would risk over heavily defended German airspace. In practice, celestial navigation was nearly useless for bomber operations. Radio navigation promised a solution. In 1942, the Telecommunications Research Establishment, a secretive British organization working on radar and radio technology, had developed two systems to help bombers find their targets. The first, called G, used radio signals transmitted from stations in England. An aircraft equipped with a G receiver could measure the time difference between signals from different transmitting stations and calculate its position to within a few hundred yards. For the first time, navigators had a reliable, accurate positioning system that worked day or night in any weather. But G had a fatal limitation. It worked on radio frequencies that traveled in straight lines, limited by the curvature of the Earth. From typical bomber altitudes of 20,000 feet, G signals were usable out to about 350 miles. That covered the Ruhr, Germany's industrial heartland just across the border from the Netherlands. But it didn't reach Berlin, Leipzig, Munich, or dozens of other strategic targets deep in German territory. And the Germans, once they captured a G receiver from a downed bomber, could build jammers to render it useless. The second system, called oboe, was even more accurate. It used two ground stations in England that tracked an aircraft using radar. The stations sent signals that told the pilot when to turn and when to drop bombs. Oboe could achieve accuracy within a few hundred feet, revolutionary for the time. But oboe had even more severe limitations. Each pair of ground stations could guide only one aircraft at a time. An oboe-directed raid required the aircraft to fly straight and level on a precise heading for several minutes during the bombing run, making it extremely vulnerable. And oboe had the same range limitation as G, about 350 miles. These systems were valuable, but they couldn't solve the fundamental problem. To bomb deep into Germany, to strike at Berlin and other distant targets, British bombers needed a navigation and targeting system they could carry with them. They needed to be able to see through the darkness and clouds to identify their targets. They needed radar. The word radar itself was American, a 1940 acronym for radio detection and ranging. But the technology was very British. In the late 1930s, as war clouds gathered over Europe, British scientists had developed increasingly sophisticated radar systems for air defense. These radars could detect incoming German bombers at ranges of over 100 miles, giving RAF fighters crucial time to intercept. The chain-home radar system around Britain's coast was one of the decisive technologies of the Battle of Britain. But all these early radar systems looked up and out. They detected aircraft in the sky. No one had seriously considered pointing radar downward and using it to see the ground, except they had, almost by accident. In the years before the war, a brilliant Welsh physicist named Edward George Bowen, universally known as Taffy, had been working on airborne radar for RAF fighters. The idea was to mount a small radar set in a night fighter, allowing it to detect and track German bombers in the darkness. Taffy Bowen's early experiments used relatively long wavelength radio waves, around 1.5 meters, which required large, ungainly antennas. During test flights, Bowen noticed something curious. When his experimental radar pointed toward the ground, the display lit up with returns. Different types of terrain produced different signal strengths. Water returned very little signal, appearing dark on the display. Open fields returned moderate signals. But cities, towns, and anything with vertical structures, buildings with walls and edges, produced strong, bright returns. Bowen realized, almost casually, that radar could be used to create a crude map of the ground. He mentioned this to colleagues. Perhaps, he suggested, bombers could use a downward-looking radar to find their targets at night. But in the late 1930s, radar technology was still primitive. The displays were crude, showing only the distance to a target, not its direction. Building a radar that could create an actual map-like image seemed impossibly difficult. The idea was shelved. Then, in 1940, two University of Birmingham physicists named John Randall and Harry Boot invented a device that would change everything. They called it the cavity magnetron. To understand why the cavity magnetron mattered, you need to know that radar works by sending out pulses of radio energy and listening for echoes. The more powerful the transmitted pulse, the longer the range, and the smaller the objects the radar can detect. But generating powerful radio waves at high frequencies was extraordinarily difficult with 1940s technology. Most radar transmitters produced a few hundred watts at best. The cavity magnetron produced thousands of watts, and it did so at much higher frequencies, much shorter wavelengths than previous systems. The cavity magnetron wasn't elegant. It was a chunk of copper, machined into a precisely engineered block riddled with cavities, circular holes arranged around a central cathode. When voltage was applied, electrons swirled around in these cavities, generating intense microwave radiation at wavelengths of around 10 centimeters. The device was compact, rugged, and produced more power than any other microwave generator in existence. The implications were immediate and profound. At 10-centimeter wavelengths, radar antennas could be small enough to fit inside aircraft. The shorter wavelength meant much better resolution, the ability to distinguish smaller objects and see finer detail. And the higher power meant greater range. When a British technical mission led by Sir Henry Tizard traveled to the United States in September 1940 to share British technology in exchange for American manufacturing capacity, they brought with them a cavity magnetron. The Americans, shown what this unassuming block of copper could do, were astounded. One American scientist called it the most valuable cargo ever brought to American shores. The United States immediately began development of radar systems based on the cavity magnetron, work that would lead to revolutionary advances in radar technology for both military and later civilian applications. But back in Britain, the cavity magnetron sparked new thinking about airborne ground mapping radar. If the magnetron could generate powerful signals at 10-centimeter wavelengths, and if different types of terrain reflected those signals differently, then perhaps a practical navigation and bombing radar was possible after all. In March 1941, a physicist named Philip D. was working on a new airborne interception radar for RAF night fighters. This system, christened AIS, used a cavity magnetron operating at what the British called centimetric wavelengths. During test flights in a Bristol Blenheim light bomber, Dee's team noticed exactly what Taffy Bowen had seen years earlier with longer wavelength radar. Returns from the ground created patterns on the radar display. But because the wavelength was so much shorter, the resolution was far better. Cities appeared as bright clusters. Rivers and coastlines showed as distinct dark lines. Even individual large buildings could sometimes be distinguished. In October 1941, Dee attended a meeting of Bomber Command leadership where the navigation crisis was being discussed. He mentioned his team's observations with AIS. The response was immediate interest. Could this be developed into a practical system for bombers? Dee arranged a demonstration. On November 1st, he flew in a Blenheim equipped with AIS radar, but with the antenna pointed down instead of forward. At an altitude of 8,000 feet, flying 35 miles from a town, he could clearly see the town's outline on the radar display. It wasn't a perfect image, but it was recognizable. And crucially, it worked in complete darkness. Cloud cover didn't matter. The radar saw right through it. Bomber Command's leadership was impressed enough to authorize full development of a ground mapping radar. On January 1, 1942, the Telecommunications Research Establishment set up a dedicated team to create what would become H2S. Leading this team was Bernard Lovell, a brilliant young physicist who would later become famous for his work in radio astronomy, but who in 1942 was focused entirely on helping Bomber Command see through the fog of war. The technical challenges were immense. The experimental AIS radar Dee had used provided only a crude indication of target direction. It showed distance accurately, but direction only roughly. For a practical navigation system, the bomber crews needed something better. They needed a display that looked like a map, showing terrain features in their proper relative positions. They needed what radar engineers called a plan position indicator, a PPI display. Creating a PPI display required a rotating antenna. As the antenna spun, sweeping its radar beam in a circle, the display would also rotate, building up a complete 360-degree picture of the ground below the aircraft. On the display screen, an oscilloscope-type cathode ray tube, the electron beam would sweep from the center outward, synchronized with the antenna rotation. Each radar pulse would brighten the display at points corresponding to echoes from the ground. Strong echoes from cities and built-up areas would create bright areas on the display. Weak echoes from water or open fields would appear dark. The result would be a map-like image, updated continuously as the antenna rotated. This sounds straightforward in concept, but the engineering was nightmarish. The antenna system had to fit inside a bomber without creating excessive drag or interfering with the aircraft's structure. It had to spin continuously and reliably under combat conditions, subject to vibration, temperature extremes, and possible damage. The rotating antenna had to connect to electronics that remained stationary, requiring rotating electrical connections that wouldn't spark, arc, or create interference. The display had to be bright enough to see in a lit aircraft cabin, yet not so bright it would blind the operator or compromise the aircraft's blackout. And all of this had to be designed, built, tested, and put into production as quickly as possible, because Bomber Command was losing aircraft and crews every night. Bernard Lovell's team worked with relentless intensity. They designed a scanning antenna mounted in a distinctive teardrop-shaped housing that would be mounted on the underside of bombers, where the ventral gun turret had previously been fitted. The housing, called a radome, was made of a plastic material that didn't interfere with radio waves, protecting the antenna from wind and weather, while allowing the radar signals to pass through unhindered. The antenna itself was a parabolic reflector, focusing the radar energy into a narrow beam. At the focus of the reflector sat a small dipole antenna connected to the magnetron transmitter and receiver. As the whole assembly rotated, this beam swept around in a circle, illuminating the ground below in a rotating spotlight of radio energy. But there was a problem, one that became apparent immediately during early tests. The radar equation, which governs how much signal returns from a target, is merciless in its geometry. Signal strength falls off with the fourth power of distance. An object twice as far away returns 1/16th as much signal. This meant that ground directly beneath the bomber, being closest, returned vastly more signal than ground farther away. On the radar display, this created a blindingly bright area right at the center, representing the ground immediately below the aircraft, while more distant features were dim and hard to see. It was like trying to navigate using a flashlight that was far too bright in the center and too dim around the edges. The solution was elegant. By mounting an angled metal plate on part of the antenna reflector, Lovell's team modified the antenna's radiation pattern. Instead of radiating the same amount of energy in all directions downward, the modified antenna radiated less energy straight down and more energy at an angle. This compensated for the distance effect. The ground directly below received less radio energy, but being closer, still returned a good signal. Ground farther away received more radio energy, compensating for the greater distance. The correction followed what radar engineers called the cosecant squared law, based on the mathematical function that described the necessary gain pattern. Later versions of the antenna would be shaped with this correction built into the reflector's curvature, but for the prototype, the simple angled plate worked remarkably well. On April 23, 1942, the prototype H-2S system flew for the first time. The aircraft was a Handley Page Halifax heavy bomber, serial number V99977, specially modified to carry the radar equipment. The flight was a complete success. The radar display showed recognizable images of the terrain below, cities appearing as bright areas, water as dark areas, with enough detail that a trained operator could navigate using the display. But the project was about to face its first tragedy. Among the team working on H-2S was a man named Alan Blumlein, an engineer from EMI, the Electric and Musical Industries Company. Today, Alan Blumlein is recognized as one of the most prolific and brilliant inventors of the 20th century. He held over 120 patents. He invented stereo sound recording, developing the system that would later be used in vinyl records. He made crucial contributions to television technology, developing key elements of the 405-line television system that Britain would use for decades. His work on electronic engineering touched dozens of fields. In 1942, Blumlein was working on the H-2S radar, specifically on the modulator circuit that generated the precise high-voltage pulses needed to drive the magnetron. On June 7, 1942, Blumlein and several colleagues were aboard Halifax V9977 for a test flight of the latest H-2S modifications. The aircraft took off from RAF Defford in the afternoon. About an hour into the flight, one of the Halifax's engines caught fire. The pilot attempted an emergency landing, but at low altitude, with one engine out and another burning, the aircraft was uncontrollable. It crashed into a hillside near Welsh Bicknor in Herefordshire. All 11 men aboard were killed instantly. Alan Blumlein was 38 years old. Bernard Lovell, viewing the crash site later, was devastated. The aircraft was completely destroyed. Burned wreckage scattered across the hillside. The prototype H-2S system was gone. More tragically, 3 of the project's key engineers were dead, including Blumlein, whose genius would be sorely missed. Lovell later wrote that after seeing the crash site, he believed it might be the end of the H-2S project. But there was too much at stake, and too much progress had already been made. The team would rebuild, redesign, and push forward. Yet even as they worked to recover from this tragedy, a larger debate was beginning, one that would eventually reach the highest levels of British government and involve Winston Churchill himself. The debate centered on a single question: should H-2S be deployed operationally, knowing that eventually a bomber carrying the radar would be shot down over Germany, and the secret of the cavity magnetron would fall into enemy hands? The cavity magnetron was extraordinarily difficult to destroy. Unlike earlier vacuum tubes, which were made of fragile glass envelopes and delicate internal structures, the magnetron was machined from a solid block of copper. It would survive most crashes intact. Even if a bomber burned after crashing, the magnetron would likely remain recognizable and functional. And once the Germans examined a captured magnetron, they would immediately understand its principle of operation. Within months, they could be producing their own magnetrons, building their own centimetric radar systems. This had profound implications. The cavity magnetron wasn't just used in H-2S. It was the heart of Britain's new centimetric air intercept radars for night fighters, systems that were proving devastatingly effective against German bombers. It was used in new naval search radars and in upgraded coastal radar systems. If Germany acquired magnetron technology, all these systems would be at risk. The Germans could develop radar detectors tuned to centimetric wavelengths, warning their bombers and submarines when they were being tracked. They could build their own centimetric radars, potentially superior to British systems. Lord Cherwell, Winston Churchill's chief scientific advisor, was particularly concerned. Cherwell argued that H-2S should be redesigned around a different technology, the klystron, another type of microwave generator that was far more fragile and easier to destroy. A klystron-equipped aircraft, if shot down, would likely leave nothing intact for the Germans to capture. The H-2S team strongly disagreed. They built a klystron-powered version of H-2S and tested it. The results were dismal. The klystron couldn't generate nearly as much power as the magnetron. Where the magnetron version could detect a city at 35 miles, the klystron version barely managed 10 miles. There was no way to improve the klystron's output enough to match the magnetron's performance. It would be the magnetron or nothing. The team also argued that the Germans were almost certainly working on their own centimetric radar technology. The basic physics was well understood before the war. German scientists were excellent. It was only a matter of time before they developed their own magnetrons or equivalent devices. Withholding H-2S from operational use wouldn't keep the technology secret for long. Through the summer and fall of 1942, as the H-2S team worked to finalize the design and prepare it for production, the debate raged. Some argued that the potential benefit to Bomber Command outweighed the security risks. Others argued that giving Germany the magnetron would be a catastrophic intelligence failure. And then, in September 1942, Winston Churchill himself made the decision. H-2S would go into operational service. The potential to improve Bomber Command's effectiveness was simply too important. Britain needed to demonstrate to its allies, especially the Soviet Union, that it was prosecuting the war against Germany aggressively. The bombing campaign had to continue, and it had to become more effective. H-2S would make that possible. Churchill's decision came with one caveat. Priority for H-2S production would initially go to Coastal Command, which was using similar radar equipment to hunt German submarines. The argument was that a patrol aircraft shot down over the Atlantic was far less likely to leave wreckage that could be recovered than a bomber shot down over Germany. Once Coastal Command's needs were met, production would shift to Bomber Command. But even as the first production H-2S units began arriving at RAF squadrons in late 1942, another technical crisis was developing. A crisis that, in its own way, was as serious as the magnetron security question. During flight tests, navigators pointed out a fundamental problem with the H-2S display. Traditional navigation charts were always oriented with north at the top. This was so standard that navigators thought in terms of north-up maps instinctively. But the H-2S display showed north at the top only if the aircraft was flying north. If the aircraft turned east, the display rotated, showing east at the top. This made navigation using H-2S extraordinarily difficult. The navigator had to constantly perform mental rotations, imagining what the terrain would look like on a north-up map while staring at a display oriented to the aircraft's heading. The solution was to add a stabilization system that rotated the display to keep north at the top, regardless of the aircraft's heading. This required connecting the H-2S display to the aircraft's gyro compass and adding an electrical system that would counter-rotate the display. Engineers at EMI worked frantically to design and build this modification. It sounds simple in concept, but implementing it reliably in 1942 was a significant engineering challenge. And once the north-up display was implemented, navigators immediately identified another problem. With north always at the top, it was no longer obvious which direction the aircraft was heading. Previously, the aircraft's heading was always toward the top of the display, but now the display was stabilized. So a heading indicator was added, a bright line on the display that pointed in the direction of flight. Then bomb aimers requested the ability to rotate this heading line manually. During a bombing run, aircraft would often drift off course due to wind. The bomb aimer needed to see this drift and communicate corrections to the pilot. By setting the heading line to the planned track to the target, any deviation would be immediately visible. Each improvement led to requests for further improvements. A system to keep the antenna level with respect to the ground even when the aircraft rolled or pitched. A correction to the display's time base to account for the non-linear relationship between antenna angle and ground distance. Better integration with the aircraft's bomb sight. All of these modifications were valuable, even necessary, but they took time to design, test, and implement. And every modification meant another variant of H-2S, another configuration to manufacture and maintain. The team had hoped to produce a single standard H-2S Mark II version, but instead, they ended up with a proliferation of sub-variants. Mark II, Mark YIB, Mark NOIC, each with slightly different features and capabilities. Nevertheless, by January 1943, enough H-2S-equipped bombers were ready for operational use. The moment had come to find out if this revolutionary radar system would actually work in combat. January 30th, 1943. 13. British bombers took off into the darkness. Handley Page. Halifaxes and Short Stirlings, both four-engine heavy bombers. All 13 carried H-2S radar. Their target, Hamburg, Germany's second-largest city and one of Europe's most important ports. These 13 bombers were the Pathfinders, an elite force within Bomber Command. The Pathfinder Force, established in August 1942 under the command of Air Vice Marshal Donald Bennett, consisted of the most experienced crews flying the most advanced equipment. Their job was to find the target, mark it with flares and incendiary bombs, and create a clearly visible aiming point for the main bomber force following behind them. The Pathfinder concept addressed a fundamental problem that had plagued Bomber Command since the beginning of the war. Even if one bomber in a raid managed to find the target and drop its bombs accurately, what good did that do if the other 99 bombers couldn't find the target? Wouldn't it be better to have the most skilled crews focus on finding and marking the target, while the rest of the force simply bombed the markers? But marking targets required being able to find them reliably, and until H-2S, the Pathfinders had no reliable way to locate targets in bad weather or deep into Germany beyond the range of radio navigation aids. H-2S changed everything. On that January night, the weather over Hamburg was overcast, with cloud cover obscuring the city. In earlier raids, this would have meant bombing blind, dropping explosives based purely on dead-reckoning navigation with no way to verify the target. But on this night, the H-2S operators could see the city through the clouds. Hamburg, as it turned out, was an excellent target for H-2S. The city sat on the north bank of the river Elbe, a major waterway that appeared as a distinctive dark winding line on the H-2S display. The Elbe flowed into the North Sea through a wide estuary that was unmistakable on radar. The city itself, built up with thousands of buildings, showed as a bright area on the display, easily distinguished from the surrounding countryside. Even better, Hamburg was a port city with docks, warehouses, and waterfront districts that created strong radar returns. The 13 Pathfinder bombers, navigating using H-2S, found Hamburg despite the cloud cover. They dropped their marker flares and incendiary bombs, creating visible fires that burned through gaps in the clouds. The 100 Lancasters of the main bomber force, following 20 minutes behind the Pathfinders, bombed these markers. Post-raid assessment judged the results as satisfactory. Bombs had fallen in the target area, not scattered across the countryside. The next night, Pathfinders used H-2S to find and mark Turin in northern Italy. On February 2nd, they marked Cologne. The system was working. Bomber Command had a reliable all-weather navigation and targeting system. But on that same Cologne raid, February 2nd, 1943, disaster struck. A Pathfinder Halifax, equipped with H-2S, was shot down over the Netherlands. It crashed near the town of Rotterdam. German forces quickly secured the crash site, and there, among the wreckage, they found the H-2S radar installation, surprisingly intact. The cavity magnetron was recovered, still recognizable despite the crash. A week later, a second H-2S-equipped bomber was shot down and captured by German forces. Now they had two examples to study. The captured equipment was rushed to German intelligence and research facilities. Engineers and scientists examined it carefully. At first, they weren't sure what they were looking at. The rotating antenna installation was obviously some sort of radar. But radar pointing downward? That seemed peculiar. Was it a navigation aid? A targeting system? German interrogators questioned the captured RAF crew members. The crews had been briefed to reveal nothing about H-2S if captured, but under interrogation, enough information emerged for the Germans to piece together the truth. This was a ground-mapping radar. It allowed British bombers to navigate and identify targets through clouds and darkness. German scientists quickly realized several crucial facts. First, the system operated on wavelengths around 10 centimeters, far shorter than any radar wavelength they had been encountering from British systems. This explained why German radar detectors, tuned to meter-length wavelengths, hadn't detected these signals. Second, the heart of the system was this strange, incredibly powerful magnetron, a device unlike anything in German radar systems. German engineers carefully disassembled one of the captured magnetrons. They examined its construction, puzzled out its operating principle, and began to understand just how effective this device was at generating high-power microwave signals. This was a significant leap beyond German magnetron technology of the time. German technical intelligence prepared a report that made its way up through channels until it reached the Luftwaffe High Command. A demonstration was arranged. German engineers had successfully reconstructed a working H-2S display using the captured equipment. Luftwaffe officers watched as an operator demonstrated the system, showing how Berlin appeared on the display, the city's streets and buildings rendered as a bright clustered area, the lakes in and around Berlin appearing as dark spots, the river Spree winding through the city. The reaction, according to British intelligence reports that later learned of the incident, was near panic. If British bombers could see German cities this clearly through any weather, at night, how could they be defended? The traditional defense in depth, which relied on cloud cover and darkness to make bombing inaccurate, would be useless. The Germans immediately began two parallel development programs. First, reverse engineer the cavity magnetron and develop German centimetric radar systems. Second, and more urgently, develop a radar detector that could warn German aircraft when they were being illuminated by British centimetric radar. The magnetron reverse engineering program proceeded slowly. German industry was already strained by the demands of war production. Developing the precision machining capabilities and manufacturing processes needed to build cavity magnetrons was a multi-year project. By the time the war ended, Germany had only produced a handful of prototype magnetrons, none used operationally, but the radar detector program was more successful. By late 1943, German engineers had developed a device called Naxos, a radar warning receiver tuned to detect 10-centimeter radar signals. Naxos was installed in German night fighters. When a Naxos-equipped fighter detected H-2S transmissions from a British bomber, it would alert the pilot and provide a rough bearing to the signal source. The night fighter could then home in on the bomber, using the bomber's own radar transmissions as a beacon. This development terrified the H-2S team back in Britain. British intelligence learned, through various sources including ultra-decrypts of German communications, that the Germans had developed a detector for H-2S transmissions. A fierce debate erupted once again over whether H-2S should be withdrawn from service. The arguments against continued use were compelling. Every time a bomber turned on its H-2S radar, it was broadcasting its position to any German night fighter equipped with Naxos. The bomber was making itself a target. Surely this would lead to catastrophic losses. But careful analysis of loss rates told a different story. Bomber Command's Operational Research Unit compared loss rates before and after the introduction of Naxos. The data showed that losses had actually decreased slightly. This seemed counterintuitive until analysts dug deeper into the numbers. What they found was that H-2S, despite making bombers detectable to Naxos-equipped fighters, was improving mission success rates so much that overall losses decreased. Bombers equipped with H-2S spent less time over target because they could navigate more accurately. They didn't waste time searching for targets or making multiple passes. Get in, identify the target on radar, bomb, get out. Less time over target meant fewer opportunities to be shot down by flak or fighters. Moreover, H-2S gave bombers a significant defensive advantage. The radar could detect cities and terrain features at ranges beyond the typical engagement range of night fighters. This meant H-2S operators often noticed when the aircraft was off course before the navigator did, allowing course corrections that kept the bomber in the relative safety of the main bomber stream rather than straying into areas where isolated aircraft could be picked off by fighters. The decision was made. H-2S would continue in operational use. The benefits outweighed the risks, but the H-2S team wasn't content to rest on their success. The Mark I and Mark II versions of H-2S, operating at 10-centimeter wavelengths, had a fundamental limitation: resolution. The detail visible on the H-2S display was limited by the radar wavelength and the antenna size. At 10-centimeter wavelengths, with the antenna size that could fit in a bomber, the radar could distinguish features that were several hundred feet apart. This was adequate for seeing cities and major terrain features, but it wasn't enough for precision bombing of specific targets within a city. Over large cities like Berlin, Hamburg, or Cologne, the H-2S display showed a fuzzy, bright blob. The city was clearly visible, but individual districts or specific industrial complexes within the city couldn't be distinguished. For true precision targeting, H-2S needed better resolution. Better resolution meant shorter wavelengths. And by 1943, British and American scientists had developed a new generation of cavity magnetrons operating at 3-centimeter wavelengths in what's called the X-band. At 3 times shorter wavelength than the original S-band magnetrons, these X-band devices would provide 3 times better resolution for the same antenna size. Development of an X-band version of H-2S began in mid-1943. The new system, designated H-2S Mark III, used a 3-centimeter magnetron and a refined antenna design. The resolution improvement was dramatic. Cities that appeared as indistinct blobs on Mark the Saturn II displays showed clear detail on Mark III. Third displays, individual districts could be distinguished. Large buildings, railway marshalling yards, and factory complexes showed as distinct features. The Americans, working in parallel, developed their own X-band ground mapping radar based on the British H-2S design. They called it H-2X, and it became operational in late 1943. The close collaboration between British and American radar. Scientists meant that improvements in one system quickly. appeared in the other. By late 1943, the combination of improved radar, experienced Pathfinder crews, and refined bombing tactics was transforming Bomber Command's effectiveness. The change from the dark days of 1941, when only 1 in 3 bombers got within 5 miles of the target, was striking. Now, with H-2S guidance, Pathfinders could reliably mark targets in any weather, and the main force could bomb those markers with reasonable accuracy. But there was one more element that would make the difference between merely effective bombing and devastating bombing. And this element had nothing to do with radar. It was called window. Window was absurdly simple. It consisted of strips of aluminum foil, cut to specific lengths corresponding to half the wavelength of German radar frequencies. Each strip was about 1 foot long and half an inch wide. Thousands of these strips would be bundled into packages. When dropped from an aircraft, window strips fluttered down through the air, each strip acting as a tiny radar reflector. To German ground radar and airborne radar systems, each bundle of window appeared as an aircraft-sized return on their displays. Drop enough window, and you could create a snowstorm of false returns that completely overwhelmed radar displays, making it impossible to track real aircraft. The concept had been known since at least 1937. British scientists understood that radar could be jammed this way. German scientists knew it too, but neither side had used window operationally, because both sides feared that deploying it would reveal the technique to the enemy, who would immediately use it against them. It was a technological standoff, each side holding back from using a weapon they knew worked, because they feared retaliation more than they valued the initial advantage. By mid-1943, this logic no longer held for the British. German bombers rarely penetrated into British airspace anymore. The Luftwaffe was focused on the Eastern Front and on home defense. Even if Germany retaliated by using window against British radar, it would affect only a handful of scattered raids. But, for Bomber Command, window could protect hundreds of bombers on every mission over Germany. In July 1943, Arthur Harris, head of Bomber Command, received permission to use window operationally. The first use would be during Operation Gomorrah, a maximum-effort attack on Hamburg. The plan was audacious. Multiple raids over several days and nights, alternating between RAF night attacks and USAF daylight attacks, would pound Hamburg repeatedly, giving the city no time to recover between raids. The RAF raids would use the full combination of Pathfinder marking with H-2S radar, accurate bombing by the main force, and window to blind German defenses. On the night of July 24, 1943, nearly 800 British bombers took off for Hamburg. As they approached the German coast, bombardiers began pushing bundles of window out of the aircraft through flare chutes. Each bomber carried thousands of bundles. The bundles broke apart in the slipstream, releasing clouds of aluminum strips that drifted down slowly through the air. German ground radar operators stared at their screens in confusion. The displays filled with returns, hundreds, then thousands of aircraft contacts. The radar showed the sky full of bombers, an impossible number. Controllers tried to direct night fighters to intercept, but the fighters reported they couldn't find the bombers. The fighters could see window returns on their own radars, but when they turned toward these contacts, they found nothing but clouds of aluminum strips. The German radar-directed night fighter system, which had been claiming an increasing toll of British bombers over the previous year, was effectively blind. Searchlights swept the sky uselessly, unable to coordinate with radar. Anti-aircraft guns fired blindly at estimated altitudes and headings, but without radar ranging, their accuracy plummeted. The Pathfinder force, guided by H-2S, found Hamburg and marked it. The main force bombed the markers. With German defenses in chaos, bomber losses were far lower than expected. Only 12 bombers were lost out of nearly 800 dispatched, a loss rate of 1.5%. Far below the typical 5% that Bomber Command had learned to expect on major raids. The bombers returned on July 25th, 26th, and 27th interspersed with American daylight raids. The combination of high explosives, which blew buildings apart and exposed their interiors, and incendiaries, which ignited anything flammable, created the conditions for a disaster unprecedented in warfare up to that time. On the night of July 27th, the third RAF attack, conditions in Hamburg were perfect for horror. The weather was hot and dry. The city's emergency services were exhausted from fighting fires after the previous raids. Much of the city's firefighting equipment had been destroyed. Water mains were broken, and when the bombs began to fall on this night, concentrated on the working-class residential districts east of the city center, the fires that started quickly merged into a single enormous conflagration. Hot air rises. This is simple physics, but when a fire becomes large enough, the rising hot air creates a self-sustaining wind that draws in oxygen from surrounding areas, feeding the fire and causing it to grow even hotter. This is called a firestorm, and once it begins, it becomes unstoppable. In Hamburg, on the night of July 27, 1943, a firestorm developed that would become one of the defining horrors of World War II. Temperatures in the fire zone reached 1,000 degrees Celsius. The updraft was so strong that people on the streets were pulled off their feet and thrown into the flames. Asphalt in the streets caught fire and burned. Glass windows didn't just shatter, they melted. People who took shelter in basements suffocated as the fire consumed all the oxygen. Those who ran into the streets were incinerated. The firestorm burned for 3 hours. When dawn broke, 8 square miles of Hamburg had been reduced to ash. 45,000 people, mostly civilians, were dead. Hundreds of thousands were homeless. The industrial capacity of Germany's second-largest city was crippled. The Battle of Hamburg, as it came to be called, demonstrated what Bomber Command, equipped with H-2S radar, window and refined tactics, could achieve. The death toll from this single week of bombing exceeded the death toll from all German bombing of Britain during the entire Blitz. The psychological impact in Germany was profound. For the first time, many Germans began to question whether the war could be won. Yet the victory came with deep moral ambiguity. The majority of the dead in Hamburg were not soldiers or war workers. They were children, elderly people, housewives. The firestorm made no distinction between military and civilian, between Nazi and anti-Nazi. It simply consumed everything in its path. Arthur Harris, the commander of RAF Bomber Command, believed that strategic bombing could break German morale and win the war. His strategy, endorsed by Churchill and other British leaders, was to target German cities with the deliberate aim of destroying them, killing their inhabitants, and breaking the will of the German people to continue fighting. Harris called it area bombing, a euphemism for what was, in essence, a campaign to terrorize the German civilian population into submission. The morality of this strategy was debated even during the war, and has been debated ever since. Defenders argue that total war required total measures, that Germany had started unrestricted bombing of civilian targets, and that breaking German industrial production and morale shortened the war, ultimately saving lives. Critics argue that deliberately targeting civilians was a war crime, that area bombing was militarily ineffective at breaking morale, and that resources devoted to strategic bombing would have been better used supporting other operations. H-2S radar didn't create this moral dilemma, but it made area bombing far more effective. Without H-2S, Bomber Command couldn't reliably hit cities on cloudy nights or deep into Germany. With H-2S, Bomber Command could strike any target in Germany in any weather. The fog of war had been lifted, and what that revealed was the capacity for industrial-scale destruction. As 1943 turned into 1944, H-2S continued to evolve. The Mark III X-band version provided the resolution needed for attacks on precision targets: oil refineries, synthetic fuel plants, chemical factories, and transportation hubs. New display improvements helped navigators use H-2S more effectively. Integration with bombing computers allowed for increasingly automated bombing runs, but the fundamental principle remained unchanged from those first flights in 1942. Radio waves, transmitted from an aircraft, reflected from the ground, received and processed to create a map-like image. Simple in concept, revolutionary in effect. The technology that came out of the H-2S program would shape the post-war world in ways the wartime developers never imagined. The same magnetron that powered H-2S found its way into a completely different application: the microwave oven. A Raytheon engineer named Percy Spencer, working on radar systems, noticed that a chocolate bar in his pocket melted when he stood in front of a magnetron. This led to the realization that microwaves could heat food, and eventually to the development of microwave ovens for cooking. Ground-mapping radar technology, pioneered in H-2S, became the foundation for civilian aviation weather radar, satellite mapping radar, and eventually the synthetic aperture radar systems that provide incredibly detailed images of Earth's surface from space. The Plan Position Indicator display, developed for H-2S, became the standard radar display format, used in everything from air traffic control to ship navigation to weather forecasting. Bernard Lovell, who led the H-2S development team, returned to academic research after the war. Using his expertise in radio technology and detection of faint signals, he pioneered radio astronomy, building the massive Lovell telescope at Jodrell Bank, which remained the world's largest steerable radio telescope for decades. The same skills that let him detect faint radar echoes from cities allowed him to detect radio emissions from distant galaxies. The Telecommunications Research Establishment, which developed H-2S, evolved into various British government research organizations that continued to advance radar, electronic warfare, and communications technology throughout the Cold War and beyond. But for the bomber crews who used H-2S during World War II, the device was simply a tool that helped them survive and complete their missions. The average life expectancy of a bomber crew member in 1943 was measured in missions, not months. Anything that improved their chances of finding the target quickly and getting home was welcome. One crew member, interviewed years after the war, remembered his first mission using H-2S. The target was deep in Germany, beyond the range of any radio navigation aids. The weather was terrible. Solid cloud cover from England to the target and back. Without H-2S, the mission would have been an exercise in futility. Blind navigation followed by blind bombing with no hope of hitting anything useful. But with H-2S, their navigator was able to track their position continuously. The coastline showed clearly on the display as they crossed from the Netherlands into Germany. Rivers appeared as dark lines, cities as bright areas. As they approached the target, the H-2S operator confirmed they were exactly where they needed to be. The bomb aimer watched the target approach on the display, centered it, and released the bombs. The entire crew felt confident they had hit the target. And on the flight home, the navigator used H-2S to track their position, making corrections for wind drift, guiding them safely back to England, despite never seeing the ground through the clouds. That crew member said something profound about the experience. Before H-2S, night bombing felt like throwing darts while blindfolded. You knew roughly where the target was, you aimed in that general direction, you released your bombs and hoped. Sometimes you got lucky, usually you didn't. After H-2S, you could see. Not clearly, not in photographic detail, but enough. Enough to know where you were. Enough to know where the target was. Enough to aim. In war, especially in the air war over Germany in 1943 and 1944, enough was revolutionary. The fog of war is a concept as old as warfare itself. It describes the uncertainty, the confusion, the inability to know what's happening even a few miles away, even a few minutes ahead. Commanders throughout history have struggled against this fog, trying to pierce it with scouts, signals, communication systems, and intelligence gathering. But the fog always returns, always obscures, always makes battle chaotic and unpredictable. H-2S didn't eliminate the fog of war. German fighters still hunted British bombers. Flak still exploded around them. Crews still died. But H-2S did something remarkable. It gave bomber crews the ability to navigate precisely through weather that would have grounded them or rendered them ineffective in earlier years of the war. It gave them the ability to find and identify targets that would have been invisible without it. It gave them, for the first time, a reliable way to aim in conditions where previously they could only guess. And in doing so, it changed the nature of strategic bombing. Before H-2S, strategic bombing was a blunt instrument, scattering bombs across the landscape with the hope that some would hit something important. After H-2S, it became a precise weapon, capable of destroying specific targets or entire cities according to the decisions of commanders. This raised profound questions. If technology gives you the power to destroy with precision, what responsibility comes with that power? If you can see through the fog of war, does that make you more accountable for what you destroy? If your aim is true, does that make the target you've chosen the right target? These questions have only become more urgent in the decades since World War II. Modern weapons are far more precise than H-2S radar ever was. Satellites provide detailed images of targets. GPS guides munitions to within feet of their aim points. Drones allow operators to see their targets in real-time high-definition video. Yet the fundamental question remains the same. Just because you can hit what you aim at, does that mean you should? H-2S was a triumph of engineering, of scientific ingenuity, of determined effort by a team of brilliant people working under intense pressure to solve an almost impossible problem. It worked. It gave Bomber Command a capability they desperately needed. It helped win the war, but it also enabled destruction on a scale previously impossible. The firestorm in Hamburg, the bombing of Dresden, the devastation of dozens of German cities. These were made possible in part by a radar system that could see through clouds. The engineers who built H-2S were not naive about this. Bernard Lovell, in his memoirs written decades after the war, reflected on the moral complexity of his work. He wrote about the excitement of solving technical problems, the satisfaction of seeing H-2S work as intended, the pride in contributing to the war effort. But he also wrote about the photographs of destroyed cities, the casualty figures, the knowledge that his creation had played a role in the deaths of hundreds of thousands of people. He didn't offer easy answers. He didn't claim that strategic bombing was unequivocally right or unequivocally wrong. What he did say was that in the context of 1942 and 1943, with Britain fighting for survival against Nazi Germany, developing H-2S seemed like the necessary and right thing to do. Looking back with the perspective of decades, the moral picture was far more complicated. This is perhaps the most important lesson from the H-2S story. Technology is never neutral. The same scientific principles, the same engineering skills, the same innovative thinking that created H-2S could have been applied to saving lives rather than taking them. Radar technology developed for war found peaceful applications in aviation safety, weather forecasting, and scientific research. But during the war, it was a weapon, and it was used to kill. The scientists and engineers who created H-2S made choices. They chose to work on military technology. They chose to prioritize its development. They chose to deploy it, knowing that it would enable large-scale bombing of cities. These weren't easy choices, and they weren't made lightly, but they were choices. And that's what makes the H-2S story more than just a tale of technical achievement. It's a story about responsibility, about the consequences of innovation, about the ways that technology shapes the world, and the ways we must grapple with what our creations enable. When those 13 Pathfinder bombers took off on the night of January 30th, 1943, carrying the first operational H-2S radar systems to Hamburg, they carried more than just a new navigation device. They carried the accumulated effort of hundreds of engineers and scientists. They carried the hopes of bomber command leadership that finally they had a tool to make strategic bombing effective. They carried Winston Churchill's determination to strike back at Germany by any means available. And they carried, though they didn't fully realize it at the time, a new capability that would change the nature of warfare. The ability to see through darkness and weather. The ability to aim with unprecedented precision. The ability to deliver destruction reliably, repeatedly, to targets deep in enemy territory. The fog of war hadn't been eliminated. It never can be. War will always be chaotic, uncertain, and brutal. But H-2S had lifted that fog enough to allow bombers to navigate and aim. And in doing so, it demonstrated both the power and the peril of technology applied to warfare. The story of H-2S is ultimately a human story. It's the story of Taffy Bowen noticing odd returns on his radar display and realizing they might be useful. It's the story of John Randall and Harry Boot inventing the cavity magnetron in a university laboratory. It's the story of Bernard Lovell and his team working impossible hours to turn a laboratory prototype into a combat-ready system. It's the story of Alan Blumlein dying in a test flight crash, his brilliance lost to a fire on a hillside. It's the story of radar operators in bombers over Germany, watching their displays and guiding their aircraft to targets. It's the story of German engineers examining captured equipment and rushing to develop countermeasures. It's the story of Winston Churchill making a difficult decision to deploy technology that might fall into enemy hands. And it's the story of the hundreds of thousands of people in Hamburg, Berlin, Cologne, and dozens of other German cities who became the targets of bombing made more effective by radar technology. People who died in firestorms and collapsing buildings, people who lost their homes, their families, their futures. People who were, in many cases, not Nazis, not war criminals, not even war industry workers, just people who happened to be in cities that strategic bombing doctrine had designated as targets. Technology doesn't make these moral choices. People do. H-2S was a tool, a remarkably effective tool, a revolutionary tool, a tool that changed the course of the war. But still, just a tool. The choices about how to use it, what targets to attack, whether the destruction it enabled was justified, those were human choices made by military and political leaders. And those choices, those questions about the morality of strategic bombing, remain unresolved. Was area bombing of cities a necessary evil to defeat Nazi Germany? Or was it a war crime, a deliberate targeting of civilians that violated the laws of war? Did it shorten the war and save lives overall? Or was it militarily ineffective, a waste of resources that could have been better used elsewhere? Historians still debate these questions. What's not debatable is that H-2S made strategic bombing far more effective at achieving its aims, whatever we judge those aims to be. The radar worked. It did exactly what it was designed to do. It lifted the fog of war over Nazi Germany, and in doing so, it enabled both the achievement of military objectives and the deaths of hundreds of thousands of civilians. This is the complexity, the moral ambiguity, the weight of responsibility that comes with technological innovation in wartime. When you create something that works, when you solve the technical problems and turn theory into practice, you also bear some responsibility for what your creation enables. The scientists and engineers who developed H-2S knew this, at least in the abstract. They were creating a military technology in the middle of a war. They knew it would be used to bomb cities. But the full reality of what that meant, the fires and the deaths and the destruction, that was something different. That was something that could only be fully understood in retrospect. Today, we have even more powerful technologies. We have precision-guided munitions that can strike individual buildings. We have satellites that can read license plates from orbit. We have drones that can watch targets for hours or days before striking. We have cyber weapons that can disable infrastructure without explosions. All of these technologies raise the same questions that H-2S raised 80 years ago. Just because we can strike precisely Does that make our choice of targets correct? Just because we can see clearly, does that mean we understand the consequences of our actions? Just because we have lifted the fog of war, does that make war itself more just, more humane, more acceptable? These questions don't have easy answers, but they're questions we must continue to ask, because technology keeps advancing, and the power to destroy keeps growing. And the responsibility for how we use that power rests with us, with human beings making human choices. The story of H-2S radar is a reminder that technology is powerful, that innovation can change the world, and that with that power comes profound responsibility. The radar worked. It was brilliant engineering. It helped win the war against Nazi Germany, but it also enabled destruction on a massive scale. And the people who were caught in that destruction were, in the end, human beings just like the people who created the technology. That's the lesson, if there is one, from the story of how a bold radar design lifted the fog of war over Nazi Germany. Technology can give us capabilities we never imagined, but it can't answer the question of how we should use those capabilities. That question, always and forever, remains a human question, requiring human judgment, and demanding that we face the consequences of our choices. On a cold February night in 1943, 13 bombers flew toward Hamburg carrying a revolutionary new technology. They could see through the darkness and clouds. They could navigate with precision. They could find their target and mark it for destruction. The fog of war had lifted, and what that revealed was both the power of human ingenuity and the terrible responsibility that comes with that power. A responsibility we still bear today, and will bear as long as we continue to create technologies that shape the world and determine the fate of millions.